Oh. All right. I'm not sure what that top one is. Anyway. So, welcome. I guess this is we'll conduct kind of a review session for the final today. I know you still got a week worth of stuff to do, individual presentations. I think Shang actually, did you delay the submissions for the presentations or not? Did you delay the submission dates for the presentations on Angel? Or they still were all given in by Wednesday? Already passed. Okay. So, no, I guess I saw some drop boxes with different dates on it. Perhaps that's for the peer review forms? Yeah. Yeah, okay, gotcha. So you've submitted your presentation, so that's going on next week, and Shang has been sending emails about that. The final is set for the Monday of finals week. It's an evening exam, 6:40. There are two rooms, but one of them seats 700 people. So we'll all send an email around, but we'll all go to 101 Life Sciences. 101 Thomas, I think it is. It doesn't matter. But it's a big enough room to get everybody in it, right? Would you do it just with one? And so 700 people is large enough to have alternate seating, which is important. And so that's kind of the final schedule. And for what it's worth, I'll come out to that as well. But I won't be here next week for the presentations, unfortunately. But I will see them online. So let me congratulate you for making it through to the end of this thing. It's been a pretty broad waterfront that we've covered, and we've covered a lot of stuff. So you should be pleased with yourself. I don't think it's a straightforward class. I don't know whether I make it easier or more difficult for you. You can decide that yourself. I think it's useful to codify some of your comments in SRTEs. That's always an interesting observation to me. Certainly you can think of those as criticism or lauding an instructor, but I view them a much different way than that. I think it allows you to have a voice in terms of what you think works and what doesn't work for you. Certainly there are two different populations in this class, those who've come out in the mornings and those who've chosen not to. I don't know what the difference is between those populations, so I'd be kind of curious. So if you do write in comments, you might actually say what population, or make it obvious in the comments what population you exist in. And so I'd be interested to know, for instance, your feelings about whether it's useful to record these and broadcast them, whether you need to come to classes, whether now that we have a whole series of these videos for every single thing that we've done in this class now, we didn't have that at the beginning of the year, whether there's another way to prosecute this class in terms of having people view those before and come to class and then do things interactively and have the students participate in the class. I know that myself as an undergraduate, I like the anonymity of classes and just being able to just go along, and if I wanted to go, and if not, fine too. And in those days, if you didn't get the notes, you'd get them from someone else and to be able to catch up, and that was just fine. So this, I don't know how big a deal interactivity is for you, so I'd just be curious to know those things. I'd be interested to know your feelings of whether there's some nefarious activities going on. Certainly, I have my, certainly, I may be a fool, but I'm not a complete moron. And I know that I would guess that there are solutions for the homeworks floating around, and there's certainly ways that you can game the system to be able to do that without ever doing the homework questions. I'm sure you've thought of those ways. Maybe some people, not here, of course, would have acted on those. So I'm kind of curious as to that. And that's why, of course, the homeworks are worth 15% and not 50%, which they were worth maybe 5 years ago. And so your impressions and comments on this, I think, would be interesting. So that's where we are. So that might be the last thing on your minds right now. You realize you have to get across the final hurdle. As I say, I think it's been a pretty broad waterfront. You can decide. Well, I think in the light of a number of years working, you might decide whether this is a class is useful to you or not. But certainly, it's a fundamental class in terms of the activities that you'll ultimately use in your own disciplines when you graduate from here. But that might be the last thing on your mind right now. So getting ready just to get the hell out of this class basically might be something that's more in line with your thoughts. So the final is on the first Monday. It's an evening final. It's just 10 minutes short of 2 hours, so it's an hour and 50 minutes. It'll be the same scoring as before, 330 points, full score is 300. There are 3 questions. And so of those 3 questions, there could be something, the topics are, instead of making it comprehensive as we have done in the past, so if you look at the prior exams, you'll see that some of them have pressure on surfaces questions. This one will limit itself to the last 3 topics. So the last 3 topics are pipe flow networks, external flows and forces on structures, and channel flows. So those are the 3 topics that the last one will be. But also, we made the point before that the one question that didn't turn up on the 3rd midterm actually will be on this. So out of the 3rd midterm questions, there were potentially questions on pipe flows, energy equation, and streamlines, right? And so you guys would know what didn't turn up on the main midterm, not the retake exam or the conflict exam. Only talking about the midterm. So I've tried to steer you in the right direction before. So pipe networks, external flows, and open channel flows are fair game on this. Plus the run over from the other one. Of course, you can look at the materials that were talked about in the 3rd review session to get some feel for that. Because basically what happened was I wrote a question on the 3rd midterm, which made the exam too long, so I just pulled it out. And so you can probably guess exactly what that would be from looking at that. So at least you're ahead of the game in that. I'm doing all the talking. Anyone have questions for me before I start going on? So I'll just review the stuff from the last 3 materials that we have, and certainly if you look at what's happened in the past, the materials that we went through in review basically encompass all the material that you'd need. You need to understand how to use it, and to use it somewhat creatively maybe, but that's basically the deal. Okay. So that's what we'll do. I'm not going to worry about that. So pipe flows. Well, we know about pipe flows. You'll never have to draw or bring a Moody chart, but you certainly know what they are now. In terms of the big picture, we've seen them also in terms the same kinds of behavior for pipe flow, which is an internal flow, and external flows. It's the same idea, right? At very high Reynolds numbers, the magnitude of this friction factor, which is a coefficient of drag, is constant, and it changes as a function of velocity at low ones, because this is viscous drag and this is pressure drag in the system, and so you know that. And so we've seen the features of that before. I put that only on because when you're dealing with pipe flow networks, you need to know a little bit about pipe flows, and this is basically the expression that you know how to use. You used it on the last exam. You know, what are the features of this? Well, the features of this are that the pump head is positive if you're putting energy into the system to pump. It's negative if you're generating electricity. The magnitude of this pump head is what? It's probably written on here. It is the power divided by the mass flow rate, Q rho G, I think, right? So I guess this is the mass flow rate times G. Pretty sure that's right. Head losses are always positive. The bag across the table, you're always, irrespective of which way you're moving, you're always losing. And the pressures, velocities, we always put this 1, we don't care about that. Elevations, so we know everything about these heads. These are at a point, and you write these at a point, and you write these as a point, and then you have to include the influence of losses in the system. Losses come in 2 flavors, so-called major losses, which are small incrementally, but over a long length of pipe they add up. Some friction factor, given by this. Constant if it's turbulent, not a function of velocity if it's not. Length of pipe, diameter of pipe, velocity in the pipe, and so-called minor losses, which you sum up, which are velocities in the fittings, per se. So these are the local velocities in the pipe or the fittings. These are the velocities at the endpoints, and so you well know how to do that. So if you use those pipe flow equations for systems, then systems come in 2 different flavors. They come either as a sequence in series or a sequence in parallel, and they have different attributes attached to them if they are in series, and that is by continuity. If you take a section anywhere across this pipe, the flow rates, volumetric flow rates, have to be equivalent to each other. And if you drew the head losses across this, of course, if you know the flow rates through the system, therefore you know the velocities, therefore you also know the head losses in the system, and you can sum those up, say, to move from A to B, because you know that the sum of the head losses has to add up to the total head loss across the system. And so that's the attributes, if you like, of a series in series, I guess. If you have it in parallel, then you know the opposite of this behavior is true, and that is that the flow rates have to sum. You have a flow in here, you have a flow in here. Because it starts off at this particular head here, and it ends up at this particular head here in both cases, the head losses in both pipe systems have to be the same. And if you had a 3rd or 4th pipe, that would have to be the same as well. And so those are the rules, if you like, for dealing with pipes. If we deal with loop systems, then the behavior is such that you can write Bernoulli between upstream and downstream and take 2 different paths. And so in this particular case, and we did one like this, you might recall that we did this one in class. And what you can do is you can write Bernoulli between the upstream and downstream. You make it easy for yourself by doing it between cases where you can get rid of the most variables. So if it's a big tank and you can write it on the surface of the big tank, you know that the pressure here is atmospheric. You know the big tank assumption would be this, and so you've immediately got rid of 2 of your terms. And of course, if you're working with the z magnitudes at each of these cases, you know the difference in the elevations. And so the solution to this is to be able to write the expression through one route and to write it through a second route. And that's what these 2 expressions are. And since they both end up at the same place, these magnitudes, since every other term within here is the same, these magnitudes have to be equal to each other. And so those 3 requirements, if you like, are the 3 requirements that you might have to have a handle on. So nothing more than that. We won't do the ones with 3 different reservoirs where you have to solve a cubic. We said that in class that you wouldn't have to do that, and you won't. We went through this one class. I won't go through it again. You can probably decide from that whether, I guess you will make informed decisions as what you will look to, maybe based on what we talk about for a long time in class. But this is a question saying if you want to increase the flow rate by 30%, how big a pipe do you have to add into the system? And so we went through that, but I'm not going to go through that again. So you can decide based on that whether what you want to focus on. And so you'll realize that there are subtle messages in here, not least of which was that we also looked at a video coming in here. So that might have something to do with what we're doing as well. External flows. You can integrate external flows around buildings and around features. I won't ask you to do that in exam. I'm not sure. Were there any homework questions that did that? Maybe there was one. I'm not sure. But we won't ask you to do that. But we will ask you to know how to use these formulae for lift and drag. Lift and drag, I guess in a nutshell, is that lift is the force that's perpendicular to the flow. Drag is the force that's parallel to the flow, just by definition. We know that. These are lift forces and drag forces as a function of a non-dimensional parameter. This is basically, as you know, lift over area. If we take these terms here, over a half rho u squared. This is an Euler number, right? This is a lift pressure. A lift divided by an area is a lift pressure. So this is just basically an Euler number, which you know, which is an important number for us to understand. So the lift coefficient is really just a non-dimensional parameter. You could think of it as kind of an Euler number. And this force is relative to an area. And it depends on what you're looking at as to what that area might be. For instance, if you're looking at drag on this wing, then the area might be the frontal area for drag, but the planiform area for lift. So you'd always be told that if that's the case, and so you need to be mindful of that. Also related to this behavior, and kind of related to this, is that this kind of division of behaviors, so you have these three regions. So you have laminar, you have transition, if you like, and you have turbulent. Those exist for external flows as well, right? It's exactly the same behavior. It doesn't matter if you're flowing on the outside of a pipe or the inside of a pipe. And so the idea is, I've lost what I was going to say now, but the idea is that if you're looking at very high flow velocities, then typically the drag coefficient is constant. This is equivalent to the coefficient of drag, basically. And also when we look at free channel flows, this is also kind of like the Manning coefficient. So there's some theme in these behaviors, whether you're looking at flow in a pipe, the friction forces on the side, flow around an object, friction forces or pressure forces on the side, and whether you're looking at a channel where you also have friction forces and loss of velocity as the mechanisms. And so I guess the point I was going to make is that when you're looking at drag, for instance, in the laminar region, this is due to viscosity. And so it's viscous drag due to the fact that the molecules of air, or typically the molecules of water, want to adhere to the structure they're going around. They have a physical drag on that to pull it across. If you're looking at these higher regimes, this is because you're killing velocity, and the drag force you have is because the velocity away from your plate is high, and at the front face of your plate it stagnates, and so there's no velocity at all. And so as you go from left to right in that plot, then you're looking at the different behaviors that you'd expect to see here. So almost all the drag force you'd have here would be due to velocity drag, because you're destroying the velocity here. If you look at a plate which is aligned slightly differently, where you have flow occurring like this, you could imagine that as the velocity changes, as you go away from this, then you get some drag force that's applied here. So you get different effects at different magnitudes. Typically, both of those behaviors are encompassed in this drag coefficient. But if the drag coefficient is just a single value, it typically means that the assumption is, which is often correct, is that the flow velocity, or the Reynolds number, is so high that you're on this right-hand side of the chart. And so as you increase the Reynolds number, the magnitude of this drag coefficient doesn't change, which means that most of the drag or the lift is due to changes in velocity. So typically that's the case for gases. So you need to know lift and drag coefficients. They're basically Euler numbers, and the area that we're talking about depends on a frontal area or a planiform area, but you would know that. Obviously the density is the density of the fluid flowing around it, not the density of the object, as you know, stating the obvious. And we went through two examples. And the two examples actually deal with the two flavors of these behaviors. And so if you look at the Moody chart, I know the Moody chart isn't appropriate for drag. Well, it is for internal drag inside pipes. We have these behaviors. So we have laminar and turbulent. And the solutions that you use to be able to solve for these are different. And these two solutions here embody both of these cases. This one is a solution for a ball falling through liquid. Sounds like an esoteric problem, but it's one of the ways in which you get grain size distributions of very fine minerals by dropping them into water and measuring the settling velocity and taking that settling velocity and calculating from that settling velocity the size fraction of the particles. And so in this particular case, the two important expressions are to do a free body diagram, weight of the particle, buoyant force, and drag force, and reconcile those with two parameters. One is the fact that the coefficient of drag is a function of the velocity, which you'd like to solve for, and also the drag force is related to coefficient of drag through this. So you can relate these two, and you can solve ultimately for the velocity, and you can look through that, how to do that. So that's for one region of these behaviors. So it's in this zone here for laminar flow. And so the reason that the solution works out that way is because the drag coefficient of drag, is a function of the Reynolds number, which is a function of velocity, and so it makes it a bit more complicated because the velocity occurs in both of these terms, and you have to work it out. If you look at the case where you have turbulent drag or pressure drag occurring, so this is viscous, and this is pressure, then the epitome of that is the hailstone example. And it's exactly the same kind of solution. You have a hailstone being lofted up inside a cloud. There's a buoyant force. There's a buoyant force acting. There's a drag force acting, and there's a weight of the hailstone. The drag force is a function of the velocity through this coefficient, right? We only use a half just out of convention because it's in Bernoulli. This is v squared a. And so now this is a bit more simple to solve. One, because the buoyant force is inconsequential because it's air and it's displacing air, so the density of air is inconsequential, so you can get rid of this. You can relate the drag force to this, and you can solve somewhat more simply than the other case because you don't have the drag coefficient being a function of velocity. So the coefficient of drag is not a function of velocity, right? It's constant. And so understanding how all this fits together for these two examples is probably worthwhile figuring out for obvious reasons. So that's kind of a important component of what we've done. Okay. So we talked about composite drag. It's really just the same as any of the other cases. It's just that you're adding up the individual contributions due to multiple bodies. So if you have a whole bunch of bodies, they have a certain drag associated with them. I suppose the basic assumption is that if you have a sphere on top of a cylinder to represent a water tower, that the flow field that results from this sphere doesn't influence the flow field around the cylinder. Of course it does, but within engineering calculations it probably doesn't affect it that much. And so that's the assumption that's used there, and is just used to be able to sum up the individual components for that. And so we didn't spend much time on that. Okay. So you'll notice this comes from very early on. So don't forget the ideal gas law. Don't forget that this is absolute temperature. Don't forget that this is absolute pressure. And that the density comes from this. And yeah, that's fine. And that's yeah. Remember the ideal gas law. So that's fine. So pipe flow networks, external flows, open channel flows. We dealt with two behaviors, and we classified them in different ways. We talked about the kinds of flows we could get would fall into three categories. We wrote the most strange category off as being off the sheet for examination. But the two flows that we did talk about, which were game, were uniform flows and gradually varying flows, right? So rapidly varying flows we talked about. So hydraulic jumps, we talked about it on Wednesday, but those are off the chart. And so the two that we can concentrate on are looking at uniform flows, and so these would be uniform flows, and these would be gradually varying flows, I guess. And the features of them are that uniform flows basically say that you have a bed that has a slope to it. The depth of water upstream and downstream is the same. Therefore, from continuity, the velocities of these flows upstream and downstream have to be the same. So the velocity heads have to be the same in each of these cases. So the energy grade line, the hydraulic grade line, which is the top surface of the water, and the slope of the beds are all equal to each other. And so that's the characteristic, if you like, of a uniform flow. And so if you have a uniform flow, you can use very simple methods to be able to calculate what that flow volume is, although we need some way of being able to figure out when it's a uniform flow, because of course when you make a channel and you plan to fill it with water, you don't know that this hydraulic grade line and the energy grade line are all going to be parallel to each other. So we need to know something about how to calculate that. So those are the two important features related to that. So in terms of uniform flows, don't have to derive any equations, but you need to probably know these two equations at the bottom. Straightforward to use, and they give you a average flow velocity as a function of a coefficient. This coefficient for SI is equal to 1, and it has units. It's the one of the few equations we've used that actually isn't dimensionally homogeneous, so it matters what units you use. This is hydraulic radius, which is equal to cross-sectional area over perimeter, wetted perimeter. And this is the slope of the bed. So the slope of the bed is equal to the elevation Z1 minus Z2 over the length over which it occurs. And so if you know the slope of the bed, hydraulic radius, and the Manning coefficient, which is so friction factor and coefficient of drag and Manning coefficients really are the same kind of thing. They give you some way of looking at the amount of losses you have in your system, typically due to friction or due to pressure drops. And in this case, it's really due to destruction of velocity, due to the combined effect of both of them. And so you can get the average velocity in a stream from this. If you multiply the average velocity by an area, then this is different only by that. The other exponents haven't changed, but you need to be able to use the right units. So you need to convert everything into meters per second. Didn't spend much time over it, but you could average Manning coefficient values, or you could divide it up into a compound channel. If you divide it up into a compound channel, of course the area over the perimeter for this would be the area, right? This box, but the perimeter, the wetted perimeter, would only be this. So you need to be thoughtful of that. I guess that's probably common sense, but sometimes it serves to point these things out. And you just need to use some magnitude, some appropriate magnitude of Manning coefficient. And I suppose actually from the way it's written, maybe increasing Manning coefficient, maybe this is really 1 over n, right, in terms of these, because this is 1 over. And so as the Manning coefficient gets smaller, there's more losses in the system. Coefficient of drag gets bigger, there's more losses in the system. Friction factor gets larger, more losses in the system. So these are all equivalent to each other in some way. So that's perhaps one of the unifying features that we have in what we've done. So friction factor, coefficient of drag, and Manning coefficient, all dimensionless parameters, which just define the losses in the system. And so this is just plug and chug. And so if you get the right magnitudes for this, then you'll get the right result. So the key word, I think, is uniform flow. So if you see uniform flow, then that keys you in on this. An example, you've certainly done these in your homework assignments to take count of these. Remember that this is not part of, the reason that this isn't part of the wetted perimeter is that the fluid that's going down in A1 out of the board or into the board is going into A2 into the board. They're going at the same velocity, roughly, and so there's no real shear between them, and so that's the reason for excluding that component. All right, so that's uniform flows. So the other component that we talked about is in terms of gradually varying flows. And so the concept that we went through were, let's not worry about this. Let's not, well, I guess let's not worry too much about this, but these are the three very important features. The idea was that we could basically write the energy equation in this form, and all we did was that we took the magnitude of, so this is Bernoulli if you like, all we did just to kind of put this in context was that we took the magnitudes of the velocities going across this upstream and downstream part, and we took the pressure at the bottom, which is just equal to the height of water above us. We took the velocity, which is going across this section, which you assumed is constant across this section, and we combined it in a term which we called specific energy. So in other words, specific energy just includes the pressure over unit weight term and the v squared over 2g term. That's all it is. And we choose to write it in a particular way that instead of having velocity in it, it importantly has the magnitude of flow rate per unit width of channel. And so this Q is equal to the total flow rate divided by the width of the channel. So that's all we did. And so if we did this, this was our one parameter which we could use to describe this behavior. And so the importance of using this parameter was that we could, when we have open channel flows, we have this problem in that we don't have a pipe which constricts the cross-sectional area of a flow. If you have an open channel, it can either flow very slowly and be deep, or it can flow very quickly and be very shallow. And so this idea of critical flow relative to the Froude number was important. So the idea was, if it's flowing really fast, it's flowing faster than the celerity wave speed, and so it can't get information upstream. Maybe that's esoteric and we don't worry about it. But the important things to think about in this are that if you look at how this energy changes as a function of depth, then you get a graph like this, where this curve here is the bounding curve, where the depth is equal to the energy. The units of energy have to be in units of length. And what you could do is, if you have a flow in a channel, you could just, for instance, change the magnitudes of this depth of channel arbitrarily. So you could choose different values of y to plug into this equation, and you'd end up with a table of values of specific depth, specific energy, and y, just by choosing y equals 0, 1, 2, 3, and you get values for E that would allow you to plot this equation, for instance. And if you would do that, the important things about this equation in terms of physical behavior are that it defines, I'm not sure what I have, I guess I have here. It defines that if you know, for instance, what the energy was in your flow between upstream and downstream, where you think that the energy should equal each other, which is always the case for gradually varying flows. It's not true for hydraulic jumps, which are rapidly varying flows, but we said those are off the map for what we're talking about here. Then you know that upstream and downstream must lie on this same line. And so if you know what the value is at one location, you can figure out that if you're able to get to this point by maybe going through this nose, to get here. We talked about this in terms of ramps, etc. So that's the importance of this diagram, is it allows you to figure out whether you're flowing slow and deep, if you're subcritical, or if you're flowing fast and shallow. But both are perhaps equally feasible for a given flow regime. And so the other things that you need to know about this diagram, none of the derivations, but you need to know that this is E critical, and at this magnitude the Froude number is equal to 1. And you also need to know that this magnitude of Y critical, so is that right? E critical is equal to 3 over 2 YC. Maybe you need that. I don't think you actually do need to know that, but you should need to know what that ordinate is. And so you just need to understand the reason for that figure, and also maybe how to use it in the same way that we've used it in class. And so you may have noticed that some of the exams that we've had have focused on things that we've done in class. So you might want to look at the examples we've done in class. This is a pictorial version of what that means. So this, if you drew this out, these relate to this flow diagram that we've just drawn. Specific energy versus flow rate. The 45-degree line, and this. And so this point here is this. And these two other points here, this would be Y2, and this would be Y1. And so the idea is that if you know what the energy is of this system, then you know what the two potential depths of flow are that could develop from this. Okay. I only say this because it gives this equation here. Actually, I don't think you need to use this equation, as it turns out. No. So, but anyway, so you know what those coordinates are. And you'll remember that we spent some time going through this in class and talking about the rationale for it. I'm looking, yeah. I'm trying to think. Yeah, okay. I thought I'd got rid of these, so let me do that now. Well, I won't change it. So I don't think you need to look at all those ones. Actually, I'll change it in the one online to not worry about those. But you should look at and understand this, I think. So if you're looking for hints and tips, then for open channel flow, perhaps you can guess there might be something. Look at the Manning formula, Shesi formula for uniform flows, but also understand this in its conceptual form. And the idea here is that if you know what the flow rate is, if you know what Q is, and you put a barrier across your stream, then and you know what the upstream flow rate is, then in this particular case, if you would draw this diagram, and so in this particular case, what do we have? Energy upstream equals energy downstream. The bed slope is 0. The slope of the fluid surface here is close to 0, and so you just have this. If you know what this is, and you know what the flow rate is, you know by continuity that the flow rate upstream and downstream have to be the same if you're not accumulating. So this has to be the case. And if this is the case, then you know what this is, but you don't necessarily know what these are. So you could do this thing where you take energy and depth, and you could plot depth and get values for energy for this. If you did that, you might be given this, or you might have to calculate it. You'd end up with a curve. And the appropriate curve up here is this curve in the middle. And so if you did this, you'd end up with this curve. And if you know what the upstream level is, which I think is the essence of this question, then immediately you know what the energy is upstream because it's this value where this intercept occurs. And this also has to equal the energy downstream. And so immediately from this you know something about what the depths would be upstream and downstream. That's all this is doing. It's allowing you to constrain it in some way. So long as you stay on the same flow rate curve, then if, for instance, the depth of this flow was actually here, then you just do exactly the same into this point. So that's all we're doing. It's saying something about the depths upstream and downstream. And of course, upstream, if you looked at the velocity of flow, you'd find that this was subcritical, and you'd find that this was supercritical downstream of this location. So just understand what these curves are. There is one question on a previous exam that talks about this. Yeah, look at this one page. That's okay. But I think beyond this, I thought I'd rip these things out. So I don't think you need this. This onwards, I think you don't need. And so I will perhaps remove those. Well, yeah, perhaps this says something about what's going on as well. I mean, this is pictorially what's going on in these systems, right? So that's perhaps useful. So I don't think you need to know all these calculations from here on in. But I think if you understand what's going on, that if you have an upstream behavior and you have a ramp, then you physically move down. You can only get to these lower regions by physically going through this nose, by having a bump big enough to do that. And we did an example like that. So if you don't have a bump big enough to get through this nose and then to be supercritical on the downstream side of it, you physically can't get to this point unless you do something like this, which forces it, right? You're putting a sluice in the way, and so by this behavior, by putting this thing here, you're forcing it to go from subcritical upstream to supercritical downstream. So maybe understand these pictures of what's going on, but don't necessarily worry about the math so much. Understand concepts. And so maybe I'll leave those in just as background. You certainly do not need to know this. Although you might be interested to know it in your future. So yeah, that's it. So how many pages? 26 pages, of which you don't need maybe the last two, so 24. So that's it. I know I've talked a lot, stuff. I mean, obviously we can't do it the same justice as we've done in class. You have the stuff online to be able to look at. Again, the deal is 3 topics: pipe networks, external flows, and channel flows. They are quite similar. They have friction factors, drag coefficients, and Manning coefficients, so they actually are tied together in a relatively logical way, but they're different in their own way. Look at past exams to get ready. Remember that the past exams were maybe comprehensive, so there isn't comprehensive stuff on here, but you should know how to use the ideal gas law. That's second nature, I'm sure, for you now. Yeah, and happy hunting. So that's good. Good luck.